All right, somebody was asking whether we do like all the solution for all the exercises. No, but we definitely do need these parts. So I'd like to do some crowdsourcing. Could somebody just shout what the polynomials for A? Somebody, please. I'd like to start with the highest power because x squared are here plus
X plus 1.
Yay. What are the factors?
Irreducible.
We already have a fancy word here. So irreducible means it doesn't split into any lower degree factors. That means the factors are just, well, this is x squared plus x plus 1. What was the order of C for that one? I saw lots of people computing that one.
3.
3? Okay. And what's the maximum period you found? 3? Did anybody find other periods as well?
1.
That's a safe bet. Now in this case we have a order 2 LMSR. So that means we have 2 to the 2, i.e. 4 states. And that means by having one period of length 3, one of length 1, we've accounted for 4 different states. So there's in his calculus. How about the next one? That was a bit larger. Somebody?
Plus x squared plus 1.
X cubed plus x squared plus 1. Factors? Irreducible, so when you try to factor it, you're getting exactly the same. So you're getting x cubed plus x squared plus 1. What was the order of C?
7.
And maximum period?
7.
Other periods? 1 is always there. And we have 1 plus 7 is 8, which is 2 to the 3. So we're good. Next one also starts with x cubed, but has more terms. So that's x cubed plus x squared plus x plus 1. Factors?
X plus 1 times x squared.
More factors.
No, x plus 1, x1? No. Yeah.
Yeah, so watch out, we are over f2. So what you said was correct, it's x plus 1 times
X plus 1 squared.
x plus 1 squared, which is together x plus 1 cubed. So for this one, I assume you all put in 1 as a root. You found that 1 is a root. Then you tried long division, dividing this thing by x plus 1, so you're getting an x squared here, plus 1. Now you have x plus 1, sorry, x squared plus 1. You put in 1, 1 squared plus 1 is 0, so 1 is still a root of this. And actually when you're having x plus 1 over f2 and you square that, then this annoying 2 times x term in the binomial goes away. So you're getting x squared plus 1 squared is the same as x plus 1 squared is x squared plus 1. So here we have x plus 1 cubed. Now what was the order of C for this one?
4.
4. And the maximum period?
4.
Other periods?
2.
1, and here 2. 1 still missing. Either something is wrong here, or we're missing another one. There's another one. When you try the all 1 state,
Yeah. Yes, there's.
and you're getting 1, 1, 1, 1, 1, 1, 1, because you're getting all 3 summed up, and so it always changes to 1. So this is the all 0 state, this is the all 1 state, and then you have the period length 2, and the longest period is 4. D. What's a polynomial? I have seen people, yeah?
X to the power 7 plus x to the power 6 plus x to the power 5 plus x plus 1.
x to the 7 plus x to the 6 plus x to the 5 plus x plus 1. Great. Anybody have a factorization for that? Now at this point, we can't just put in 0 and 1 and say, oh, doesn't factor. This thing is a degree 7 polynomial, so this can factor in all kinds of worker ways. It could factor into a degree 2 polynomial, another degree 2 polynomial, another degree, and a degree 3 polynomial, anything where the degrees add up to 7, and there is no degree 1 polynomial. So just saying that if you put in 1, you're getting 1, so not a root, is not enough. Anybody has a factorization? So this is the point where I expect you not to do it by hand anymore. Yeah?
X cubed plus x plus 1.
X cubed plus x plus 1. Here we have our degree 3 polynomial.
And x to the power 4 plus x cubed plus 1.
Now assume you did this by computer.
Yeah.
Which one you used?
Wolfram alpha.
Okay, so Mathematica says this is done. If you by some magic would have guessed that this is a factor, then you still have to figure, then you do a long division, then you still have to figure out whether this one and this one split further or not. Now, for degree 3 polynomial, if you have any way of splitting it, it could split as 1, 2, or 1, 1, 1, but you will definitely have a linear factor. So if a degree 3 polynomial splits any further, it must have a root. Now this thing, if you put in 0, you get 1, if you put in 1, you get 1. So this one doesn't split further. But starting with degree 4, you can't predict what happens. The only thing you're seeing is there's no linear factor. So for degree 4, there could still be 2 quadratic factors. The only quadratic factor which is not further factorable is this one, so you could do a long division seeing, does this one have this as a factor? Answer is no. Well, that gets very cumbersome, so we need to get some more machinery. But luckily we have computer algebra systems which help us in finding the machinery, so this is a complete factorization. What are the order of C in the maximum period? I heard some very interesting things, so apparently MATLAB has a known bug there. There's something more to, not really doing consistent stuff, so Gustavo was searching the web, but I saw lots of people who actually got it right. What's the order of C? It's not 1, it's just the first digit. 105. Now, we're expecting to find 128 states. 105 does not cover everything. What are the other ones? There's certainly, oh sorry, maximum period, you probably also found 105. Alza would be very surprised. What's missing? 1 is missing. Anybody did this? This is something you let your computer do. You don't want to do this by hand. If you haven't done this, you don't know how to do it. You put in your vector of length 7, the 0, 0, 0, 1. And then tell your computer in a while loop to update it with this function function as polynomial until you hit again 0, 0, 1. So then you start entering a period. Okay, for that one, we're finding 105. Now you can either say, well, 128 is small enough, I'll just let my computer do this for all things, and I discard 105 times the 105, and then I find a few other ones. What other numbers do I find? I find the 1 from the all zero state. Anybody saw more? Nobody got this far? Okay, you should have found a 7 and a 15. Quick sanity check, 105 plus 15 is 120, 127, 128. So that covers all of them. Now E. Polynomial, please.
X to the 10th plus x to the 7 plus x cubed plus x plus 1. Cubed. Squared, sorry.
I don't have the sheet in front of me, so I I need majority votes here. Is that okay? I also have to go back to my sheet.
Yes, it's great.
Looks good. Anybody got the factorization? Yeah?
I got x squared plus x plus 1
Okay.
squared,
Mhm.
and x to the power 6 plus x to the power 4 plus x cubed plus x plus 1
X to 6 plus x4 plus, sorry,
cubed
x cubed
plus x plus 1.
plus x plus 1. So if you want to train your computer to do this for you, so mathematically you tell it, here's a polynomial, take this modulo mod 2, and then just ask it to factor. If you're in Sage, then you build yourself, so in Sage, you build yourself a polynomial ring over the integers is it integers mod or is it integer mod? I think integer mod, right? I need my cheat sheet. Somebody has a cheat sheet. This is like this uppercase and you were looking at that. Integer mod? Okay. So in Sage, this one says that everything is to be taken mod 2. This one generates a polynomial ring, and then you tell it that this is the invariable x. Now, from that point on, whenever Sage sees x, it knows that the coefficient in front of the x is to be taken mod 2. So I was explaining a little bit. So Sage is basically Python. So all the for and while loops look very familiar if you've seen Python before. And it is like a strongly typed language. So at every moment it knows what this thing belongs to. So it knows that x, when it sees an x, then that means we're in this integers mod 2 as a coefficient. So it's very nitpicky if you suddenly say, oh, but I see it's an integer, and you want to forget about the mod 2. Then it goes like, no, this thing is a mod 2. It carries around a function mod 2. But for these things, it's very, very convenient. You just tell it, well, here's a polynomial. Since it has x, it carries around the mod 2 automatically. And then you say factor of that thing, and it factors it. I saw a few people who got the period of C.
310.
310 is larger than what I've seen so far.
126.
126. Now the weird thing is 310 is not a multiple of 126. So then I'm wondering what went wrong. But shall I do a majority vote? Anybody else got 310? 126 multiple times? Okay, I see a majority for 126. That's also what I got. I'll be happy to look in the break. Maybe there's like one entry in your matrix which is not the same. It's a little finicky. I mean, if you just mess up one of the entries, you get a different number. So this would be 126. Anybody did the maximum periods?
126.
126 is a good guess. Now I don't know whether you're just assuming it's correct or you did it. Did anybody have more periods? I mean, there's a lot missing. You've seen that 126 is a lot smaller than 1024. So from the 10 here, we know there's 2 to the 10, so 1024 states. And we have only accounted for 126. So the first exercise ended with asking you, do you have any way of speculating a relationship between those things there? Now, one thing which I heard from many of you is, well, on Monday we already had in class that the order of the matrix is a multiple of the maximum period. And here we're actually seeing that those values are typically equal. So we're getting one hypothesis that these are equal. But that doesn't tell me much yet about how to predict it. I mean, this computing the order of C is something which, well, depending on a computer algebra system, is actually quite a mess, and you don't want to sit down doing that all the time. So do we have another hypothesis? Do we see something about, say, the factorization pattern and the order of C? I mean, the first two I gave you some which didn't factor any further. Then I gave you some which factored in some funny ways. I'll leave it here, so we'll come back to that. I mean, one thing to notice is for those two cases where it didn't split any further, we're getting the maximum periods. So you could hope that if you have something which doesn't split any further, it would always be maximal. That's unfortunately a little optimistic. It will be a necessary but not a sufficient condition. However, you can actually see a bit more. Cases with repeated factors like this one with the squared in the first part and this one with the cube here are a little nasty to predict. This one is an interesting one. When you look at this thing and the factors and you see at the maximum periods, do you notice something? Sorry, the maximum and the other periods.
If you multiply the other periods, you get the max period.
If you multiply the other periods, so I skip one because it doesn't matter, so 7 times 15 is 105, that is correct. Would I be able to expect the 7 and the 15?
You have like the order of x to the power 3 plus x plus 1 is 7. Because we...
Well, we did almost
Yeah.
yeah.
It's
Okay.
7. And the other one is 15 because it's 2 to the power 4 is 16 minus 1 is 15. And
So we could test whether these polynomials would ever actually give us 7 and 15. Now for this one, yeah, whether you count from the left or from the right, they would have the same order. So these we have done. This one we haven't done, but if you sit down and do it, it will give you 15. So we actually get some sort of hypothesis that if you have different factors, we will see each of the orders over here, and we'll also see the product. That's a good hypothesis, and we will come back to why this could be the case, or do you already have a speculation what it means? Right, remember we're coming from pictures like that. What would it mean to have like an overlapping, like a product of things here or something of period 7 plus something of period 15? Okay, so I'll leave this part for the rest of the first lecture. There were some other exercises on the sheet. For the second one, I made a typo. If you reload the page, it is now fixed, so it's not alpha to the j plus 1, it's alpha to the j minus alpha to the j bar. And there's also a square root of 5. Or in general, and that will help with exercise 3. this would not be just divided by square root of 5. This is alpha to the j minus alpha bar to the j divided by alpha minus alpha bar. So for the example that you're seeing in that case, the alpha minus alpha bar is exactly square root of 5. So when you do that one, you see this. If you're doing the next one, you should see that. Then one of the questions I got is, what does it even mean to do this for F2? So one group of students was looking at this polynomial here, the x squared plus x plus 1, and was saying, well, we just said it doesn't have roots, right? It doesn't factor any further. Now, something that you should have seen in either the algebra course, so 2WF50, or in the algebra for security, the 2WF90, is, so this is exercise 3. What would alpha be for F2? So the thing to think about is that up here, your square root of 5 is also not a rational number. You have been leaving the rational numbers and you've gone to the real numbers. You've added something from that 5. So in algebra, which would be the 2WF50, or 2WF90, you saw extension fields. So if you wanted to create F2 squared, then you went for the polynomials over F2, modulo an irreducible poly. So if you haven't seen this thing yet, it's probably confusing. So if you have seen it, then the next thing should make sense. So call alpha and alpha bar the roots of, say, x squared plus x plus 1 in F2 of x modulo x squared plus x plus 1. And I mentioned before, oh, irreducible is a fancy word, so I should say what irreducible means. So we have some field, so we have a polynomial f of x where the coefficients are in some field k. So this is the set of polynomials with coefficients in k in variable x. This thing is irreducible. And it's important where we're talking, so it's irreducible over k. Irreducible of polynomials is about the same thing as prime for integers. Now, when you have a prime number, you can define this in two different ways. You can say a number of prime if, when you try to factor it, then one factor has to be the number or the negative of the number. So 7 is prime because any way of splitting 7 over the integers will give you 7 times 1, or minus 7 times minus 1, or the other order, minus 1 times minus 7. So, similarly, for polynomials, we say polynomial is irreducible if any way of factoring means there's a polynomial and a constant. For the integers, we have plus and minus to play with. Just because you could say -7 and -1 doesn't mean that 7 would be prime. It's not a nice factorization. For polynomials, well, if you're over a larger field, say you're over the rational numbers, you can always divide by 2. You can always divide by 3, just getting quotients. So we can't say that that would be a factorization. So the degree of f shouldn't change. So polynomial is irreducible if any factorization of f over k. So you divide f of x as g of x times h of x as g of x, g as a polynomial is just a constant, or h is just a constant. Now over f2, in this case, you don't notice this because the only constants you have are 0 and 1. Well, dividing by 0 doesn't make sense. Dividing by 1 doesn't change it. But if this was a larger field, then you could pull out constants, and you still would call this thing irreducible. So for exercise 3, if you want to try this, an irreducible polynomial is exactly one that doesn't factor further, so this one, or any of the entries in the parentheses. So if you have an irreducible polynomial, you can build larger fields, and then similar to how you would say in the Fibonacci example, that if you take the polynomial x squared minus x minus 1, those roots will have 1 plus or minus square root of 5 over 2. Well, square root of 5 is not a rational number. You have to leave the rational numbers to be able to take square root of 5. Here you have to leave the f2 elements in order to have a root of this. Now the only thing you know about this root, let's call it alpha, is that when you take alpha squared plus alpha plus 1, you're getting 0. Well, that's enough to actually do this exercise. So when you're then taking, say, alpha, in analogy to up there, you're taking alpha squared minus alpha bar squared, then each of those alpha and alpha bar satisfies that the square of it is the linear term plus 1. So if we're doing exercise 3 for x squared plus x plus 1, then alpha and alpha bar satisfy alpha squared plus alpha plus 1 is the same as alpha bar squared plus alpha bar plus 1, and that's 0. So if you're taking j equals 1, well, it's kind of boring because we have alpha minus 1, alpha minus alpha bar to the 1 divided by the same thing, so you're getting a fraction of 1. We're getting alpha plus alpha bar divided by alpha plus alpha bar is 1. Now j is 2. Now it gets more interesting. So if alpha squared plus alpha bar squared divided by alpha plus alpha bar. Now I actually need to do some work. I plug in that alpha squared is the same as alpha plus 1. The first part. And then alpha bar squared, well, if this thing is 0, then alpha bar squared on this side is equal to alpha bar plus 1. That's now the numerator. And then the denominator is alpha plus alpha bar. Okay, what's that? Yep, 1, because the 1 plus 1 gives me 0, and I'm left in the numerator is alpha plus alpha bar divided by alpha plus alpha bar. Okay, so when you do this all the time, then you're getting here your sequence of numbers. In order to make it, well, one is still missing, let's do the j equals 3. Then we have alpha cubed plus alpha bar cubed divided by alpha plus alpha bar. Now we know already that alpha squared is alpha plus 1. Now alpha cubed is exactly 1 times more multiplied by alpha. So I'm taking this thing here times alpha. So I'm getting in the numerator, I'm getting alpha squared plus alpha bar squared plus alpha bar divided by alpha plus alpha bar. Alright, at this point I can't see anything yet. So I have to do one more round of simplification. I'm replacing alpha squared again by alpha plus 1. There's another plus alpha. I'm replacing alpha bar squared by alpha bar plus 1. There's another alpha bar. I divide by alpha plus alpha bar. And I get what? I hear some whispers.
0.
Was a louder whisper, I hear 0. Yes, all of those nicely cancel, and the ones cancel as well, so this is 0. And we know that for this one, the period is 3, so if I go for j equals 4, I will get 1 again, 1, 0, 1, 1, 0, which is the same as the output sequence of this, just shifted by something. So this formula that we suspect from the Fibonacci sequence doesn't care about our initialization vector, so it could be shifted. So this gives 1, 1, 0 as a period, which is shifted. I told you to start with 0, 1, and then is probably what you got. So using this formula gives you a periodic sequence, which is matching your sequence, but it doesn't take as your input where you should start. The other 2 exercise parts are going back to the lecture notes for Monday and figuring out all the details. I'll leave that for you as exercise to do by yourself. There were some questions about what this whole polynomial and matrix and whatever business is. So I mentioned some words, and I should do a quick primer on matrices. So I think all of you have seen matrices. For computer science, I think it's easiest to think of it as an array. Like you have a 2-dimensional array, you have each row is an array, and then you have an array of arrays to get the matrix. And that gets you pretty far. I mean, that allows you to do a whole exercise here, but then I start to talk about eigenvalues and characteristic polynomials, and that's then kind of incomprehensible. So I should at least explain what these words mean. So, special definition. Let's see. B R n times n matrix over some field. Okay. Now, for our exercise here, it's just a matrix as long and as high as the length of the shift register, it's the order of the elements are, and the field is F2. There's something important here. If you have seen matrices in an effort to solve linear systems, here we have a square matrix. So eigenvalues, eigenvectors, characteristic polynomials, they all want to have that we have a square matrix. As many columns as we have rows. So here you had a 2 by 2 matrix, 3 by 3, and so on. Okay, so let that be an n matrix. An eigenvalue and we'll for now first say an eigenvalue is in the same field K. Well, eigenvalue is an element lambda in this field for which there exists the vector and we want that the vector is non-zero. V, and it's a length k, length n vector, such that if you multiply V by this matrix, okay, so that's something we've done on Monday. We're taking our state vector times the square matrix from the state, and we're getting another vector. Well, some vector. The interesting thing about an eigenvalue is that we're getting a multiple of the original vector. So we're getting lambda times V. So normally, when you think of matrix multiplication and you're doing this over the reals or something, you have a geometric meaning by it, then you have a linear transformation, you have a vector which points in this direction, you multiply by a matrix and it points somewhere completely different. The special thing about eigenvalues and then also eigenvectors, what we call an eigenvector, is that matrix multiplication for some special elements takes the vector and gets something in the same direction. It might be longer, it might be shorter. That is what lambda rules, whether it's longer or shorter, but it's in the same direction. So then lambda V is called the eigenvector. Called an eigenvector. And we also allow our eigenvalues and eigenvectors to be over extension fields. So note, we allow lambda and V to live in extension fields. Okay. So you have a field, in our case F2, and then you have these special things running around. Now, where do these things come in? I was talking about the characteristic polynomial, and I was saying we get this by taking the determinant of the matrix minus x times the identity matrix. Now, the relation is what we have here. So the relation to the characteristic polynomial is if you move things around, then we have that V times lambda, and you move the C on the other direction, is 0. Now, okay, lambda is an integer, C is a matrix, so to make these fit the same type, we put an identity matrix here. So now these things make sense. And it is like if you take V times lambda times I, that is just turning every entry of this V into lambda times the entry. And then the 0 here is the all 0 matrix. And so then the last part to link this up to the polynomials that we were looking at is, well, we don't know what this v will be. But we're looking for values, well, v is non-zero. That's the only thing we know about v. So if this whole thing should be 0, it must be that this guy is 0. So we're looking for lambdas so we can subtract this thing absolute. So because v is not the all 0 vector, we're looking for ways that the product can turn 0. And so we're looking now, instead of having variable x, we're having variable lambda. This means that the determinant of lambda times the identity matrix minus c is 0, which is the same as our characteristic polynomial p at lambda. Okay, this was one quick rush through matrices. We are not going to use eigenvectors and eigenvalues anymore. It's just because I used them, I figured I should define them. Monday I just wanted to get to something so we could do the exercise. So I was like, okay guys, I'm very sorry you haven't seen this before, but we need to get to some stuff so we can actually do some meaningful exercises. So here is some filling in of the pieces that are missing. So what I expect you to remember is if I give you an L of S R, then you need to know how to get the characteristic polynomial. You need to remember how to get the matrix. And then you'll need to know how to compute the order of C. For all we know, brute force. But I don't expect you to remember like how we get there. If you're interested, please do the last two exercises because that will really remind you of how to compute those things. And for that one, you do need this expression. But for using things, we don't know these. Need these. I've also asked a few of you to draw the LFSR. There's also something you should remember. And then stuff we do now. So this is not a complete list. Don't tell me, hey, you said this is all I have to remember. No, this is everything you have to remember until now. We will, after the break, do some more things that I also expect you to remember. In particular, on Monday I was promising I'll drag you through this characteristic polynomial, big matrices and determinants on the blackboard, because it will help us. We currently have some suspicion that we can learn something about the polynomials, like we just have to write this polynomial, we do the factorization, and then, there was some magic relation between this thing and the 7 and this thing and the 15. Once we've formalized it, it will be much easier to analyze an LFSR. And more importantly, we will know what to look for in building one. One thing seems to be, if you want maximum, it has to be irreducible, because if our theory is correct, then having a split thing will always mean there are some smaller ones. It will never be the maximum. It will never be just one long period and one. If it splits, you always have this period and that period. Okay, first of all, break till 45.